Hello, everyone. So I am going to start session 24. Starting from this session, in the next three sessions, we're going to focus on the chapter 12, which is on the simple regression analysis. And hopefully, so this will be the last kind of major chapters which we're going to cover in this course. And then hopefully you're going to be able to see that a lot of connections of what we have done in this course, such as random numbers, the normal distribution, fitting method, like such as the least square method or the maximum likelihood method. And also you would be able to see like the dependency, correlation, coefficient, covariance, and then also conditional probability, and also the hypothesis testing and the confidence interval. So the linear regression analysis is a kind of very rich statistical topic, and then a lot of work has been done. And I believe that this is very useful topic. And then what hopefully you would be able to learn through this three sessions on the regression analysis is to connect the different pieces of kind of technical information into kind of a consolidated topic, which is the linear regression. Okay, so let's have a look at the basic fundamentals of the linear regression analysis. So I'm sure that you have done using, for example, like if you have a two set of data, X and Y, and then like you want to fit the model. So essentially this is the most fundamental, the basic polynomial, yeah? So Y is equal to A plus B times X, yeah? So that, and then you can do this analysis essentially, like if you have two set of data using Excel, for example, you can fit the linear line. Yeah? So it's relatively simple, but it might be good to have a look at the this simple linear regression analysis, or the curve fitting, linear line fitting, from the statistical perspective, by looking at the random numbers, random variables, normal distribution, etc. So that's going to be our focus in this session. So regression analysis is the part of the statistics that investigates the relationship between two or more variables. But like for this case, we're going to look at the simple linear regression. So we're going to focus on the two variable case. And in the relation between the two variables would be linear, which means that Y is equal to A plus B times X. Yeah? So in this context, the X is said to be usually as a statistical term, independent or explanatory variable. And then the Y is said to be, or referred to as the dependent or the response variable. So the Y is to something to predict, and then the X is going to be used as a function of X. Yeah, as a in the regression analysis. And then specifically, we're going to look at the linear relation between X and Y. Yeah. And it's important that both X and Y are indeed random variables. Yeah. And then we try to capture those uncertainty in those data, X and Y, as a part of this regression analysis. So that's going to be the focus of this session. Yeah. So in a simple linear regression model, Y is equal to beta naught plus beta 1 times X, and then plus epsilon. Yeah, and then this epsilon is the error term, regression error. Yeah? And then this regression error term is usually assumed to be independent observation from the standard normal, the normal distribution with zero mean, and then a variance of sigma square. So this assumption found to be very reasonable. So the normal distribution is applicable for various regression analysis. So if we interpret this simple linear regression model, if we have a particular fixed value of X, then if we take the expected value of Y, yeah, which is here, the expected value of Y is simply if we apply the the formula we went through, we had looked at for the expected value operation. Yeah, then we can obtain the constant is simply just constant. Yeah, and then we can apply only for the x. So expected value, and then the expected value of epsilon is 0. So we can simplify this into this. Yeah. And then the variance is the same. So the variance of constant is 0, and then the variance of sigma epsilon is a sigma square, so the left with sigma square. So the interpretation from the probability distribution perspective is that the y is normally distributed with the mean value of beta naught plus beta 1, and then the variance of this sigma square. Yeah? So this is the probabilistic interpretation of the regression analysis. So graphically, what we are what we have seen is that essentially the y and then x are related, and then this is a linear relation as specified in this regression line. So y is equal to beta naught plus beta 1 times x. Yeah. So x is the explanatory variable, and then the y is the response variable. Yeah. So then, but like when along this predicted mean line is a variation distribution of randomness of this y response variable, yeah, around the predicted value, and then that has a constant value standard variance of sigma square. Yeah? So that's the interpretation. So this variance doesn't change along the value of x along this regression line. So the idea of this linear regression analysis is to obtain the values of beta naught and beta 1, and then we make some sort of statistical inferences on beta naught and beta 1, but more focus, we're going to focus on the slope parameter beta 1, because the slope essentially captures the dependency between two random variable x and y. Yeah, so that's going to be the most important aspect in the regression analysis. So beta naught is just simply the constant. So the interpretation of those two coefficients, beta naught, is the intercept. Yeah? And then the beta 1 is a slope parameter. So essentially it will capture the dependency between x and y. So if the value of x changes, say 1 unit, how much changes is expected in y. So that is the beta 1, which is a slope parameter. And then the error variance, sigma square, can be estimated from the data set. And then we assume that the error variance does not change. Yeah? So the probability distribution of the errors are constant along the regression line, yeah? As we saw in the previous graphs. And then the and then if the epsilon or the sigma square is less, then we have less variance or the variability along the predicted regression line. So which might be more preferable. So you're going to have a more accuracy in prediction. So the graphical interpretation of the slope parameter beta 1 and then error variance sigma square is that if the beta is positive, then that's a linear positive dependency. If it's 0, then the x and y doesn't, or y doesn't depend on x, and then we can have a negative correlation between x and y, yeah? When beta 1 is negative. Okay. And also the interpretation of the error variance sigma square is that if the data is are scattered around the regression line, then the error variance tends to be larger. Yeah? If the data is clustered, distributed around this regression more closely, then this is the variance is less. So that's the interpretation of those error variance. So the one important thing before we proceed is that what we try to capture in this regression analysis when we use the linear relationship between x and y, then it's we're focusing on the linear relation. So first, it's good to check whether such linear dependency of x and y is expected. Yeah. So if you have the data, then I would strongly suggest to plot the data first, x and y, and then see if you see such kind of linear trend. And if you don't see this kind of linear trend, and then there's several ways uh, to do the analysis, but we're not going to cover such um, methods. But the one way to do is to transform the data. So we could sometimes take the log or the power or exponent. So we can transform the nonlinear behavior, nonlinear relationship into linear relationship through such kind of monotonic kind of transformation. So that's one way. The second way would be more general. We assume that the relationship is nonlinear, and then we assume some sort of the functional form, and then we fit the nonlinear relation directly to the data. So, but we're not going to cover those aspects. Yeah. But the point I just want to make here is that there are many other ways to do, but it could be, for the time being, we're going to focus on the linear relationship. So let's have a look at this one example. So arsenic level of in drinking water. So this kind of chemical is very toxic, but which we can find in the groundwaters or surface waters. Yeah. So we want to make sure that those kind of arsenic contents is relatively low, especially in the drinking waters, because they would be harmful to human beings. Yep. So that have was found to be have some relationship between the pH level, so acidic level of the water. So this once we have the data, then if we plot the data, then we might be able to see this kind of linear tendency. So as the pH increases, this percent of removal of the arsenic would be smaller and smaller. So such kind of relationship might be detected by just first plotting the data. And then once you detect this kind of relation, then we can start to fit the linear curve, linear line to this data set. Yeah. Another example, stress level and then a failure time. Yeah. So we usually, like, if the stress applied to the material is larger, then the time to failure tends to be shorter and shorter. Yeah. So we expect that there's some sort of negative relation, and then this can be represented as the y is equal to 65 minus 1.2 times x, and then the variance was found to be 8. Yeah. So assume that that is the suitable relationship between the time to failure y and then the applied stress level x. Yeah. So then we might want to see how we can use this linear regression model. Yeah. So for example, when the x1 x takes the value of 20, then the mean value of the y can be calculated as 41, and when x2 is 5 unit larger, say 25, then the y2 mean value is calculated as 35. Yeah. So in that case, what would be the probability that the y exceeding 50, for example, can be calculated, because this is the normally distributed. So once we know that the threshold value of y, and then this is the exceedance probability, and then the y is normally distributed, so we can calculate the value of z. Yeah. So 50 is the threshold value we are looking at. Mean value at 20 is 41. Variance is constant as 8. Yeah. So the standard deviation is constant, 8. So we can calculate the value of z and using the z table. Yeah. And this is because this is exceedance probability, 1 minus the value of z. Yeah. CDF value of z. Yeah. Then we can obtain that's about 13%. We can do the same calculation when x2 is 25. So the threshold value we are looking at is the same, 50, but the mean value is decreased. Yeah? But the variance, the standard deviation, is the same, constant. Yeah. So 1 minus CDF value of this value of z 1.88, then which is going to be about 0.3%. So graphically, what we have looked at is that there's a linear relation between x and y, which is decreasing with this slope minus 1.2. Yeah, and then there's a variability around this regression line, and we looked at the value of x and the value of y, and then what we tried to calculate was the probability of y exceeding 50, which is threshold level around here. Yeah. So when the x is equal to 20, there's a more chance that the y taking the larger value. Yeah. When the x becomes smaller, because of the negative relation, essentially this probability distribution is shifted down, slided down. Yeah. So the chance exceeding this y is equal to 50 is less than before. So that makes sense. So we can also have a look at the calculate other types of probabilistic quantity, and then one quantity that might be of interest might be y2 minus y1. Yeah. So the difference of the two predicted values. Yeah. And then because y and then y1 and y2 both are normally distributed. Yeah. And then so the difference is also normally distributed. Yeah, with the expected value mean of minus 6, which is the difference of the mean value, and then the variance. These are x1 and y1 and y2 are independent, so we need to sum those. So the variance would be 2 sigma square. Yeah. Once we have the mean value and then the variance of the y2 minus y1, then we can do probabilistic calculations. And so the probability that the y2 is greater than y1 is simply the threshold value looking at 0, that's the mean value, yeah, divided by standard deviation. Yeah. So then again, this is exceedance probability, so 1 minus CDF value of the calculated z value. Yeah, which is about 30%. Yeah, so y2 is likely to be greater than y1 with about 30%. Yeah. Okay, so what we have seen so far was how we interpret this linear regression line, and under the assumption that the epsilon is normally distributed, then we can use the normal distribution to do various calculations as we saw. Yeah. So now we're going to focus on how we obtain those coefficients. Yeah. So in the previous case, the beta 1, beta naught, and beta 1 was assumed to be known. But again, now we try to estimate or calculate those slope and then intercept from the data. Yeah. So by setup, we have the two random variables, x1 to xn, and then a y1 to yn. Yeah. And then the idea of fitting the curve to those points is that we try to minimize the vertical distance deviation between the line we're going to fit and then the data point we have as observation. And then we minimize the sum of squares of the vertical deviations. Yeah? So that is essentially called as the least squares method, which is very standard. The minimization of the squared error, differences between the data point and the fitted model line. Yeah? So the objective function to be minimized from mathematical point of view is the sum of the data here. Yeah? Y1, which is the data point, minus the predicted value of the regression model, if beta naught and the beta 1 are known, but those beta 1 and beta naught are the one to be determined as a part of this minimization. Yeah? So this can be also said as written as the sum of squared error is going to be minimized. So this is the general kind of mathematical problem of the linear least squares fit. So graphically, idea is that if we have some hypothetical the line, say beta naught and beta 1, given this value of beta 1, beta naught and beta 1, we can fix this line. Yeah? And in the given the data, we can take the difference, vertical differences between the data points and in this linear line, and then we take this squared sum. Yeah? Take this first the difference square, and then take the sum over the entire data set, and we try to minimize. Yeah? So we adjusted the value of beta naught and beta 1, yeah? Such that this error, squared error, is going to be minimized. And then least square method, especially for the normal distribution case, normal error case, can be linked to also the maximum likelihood method, which we also seen in, I think, chapter 7. Yeah. So there's usually the two methods, the least square method, and then also the maximum likelihood method. And then both are the very popular methods. For the linear regression case, we can achieve the equivalence between the least square method and then the maximum likelihood method. So that's one thing I think it's important things to know. So under the, again, regression analysis, simple regression analysis, for which the error, regression errors are normally distributed. For that case, the least square method and then also the maximum likelihood method would give the same answer or the equivalent. Yeah? So to see that, the y we're gonna model is normally distributed with the mean value of this and then the variance of this. Yeah? And then if we write down the likelihood function, yeah, of the n independent sample, yeah, can be written as this one. Yeah, and you see here, it's exactly the same expression as in this equation, yeah, which is based on the least square method. Yeah, and then we try to maximize this likelihood function. Yeah, and then we usually do log likelihood, take the log of likelihood function. Yeah, so the multiplication becomes essentially just a summation, and then we maximize this function with respect to beta naught and beta 1. So this term is just a constant. Yeah, so it doesn't matter. So essentially, it comes back to minimizing this term, these differences. So that is why the least square method and the maximum likelihood method is equivalent. Yeah. So coming back to the least square method, if we have the objective function Q, yeah, which is defined previously, and then what we're gonna require to obtain the minimized point is that we take the partial derivative of this objective function Q, yeah, squared error difference, sum of squared error difference, with respect to two model parameter beta naught and then beta 1. Yeah, so we have two equations, two parameter. Yeah, and then if we set those to 0 and then solve for beta naught and beta 1, then we can determine the best fit values of those coefficients, yeah, under least square method. And then those equations are usually called as a normal equation. And then like if you set this to 0 and then just like do some mathematical manipulation, essentially what we get is this equation. Yeah. So once you have the value of y, which is data point, and x, and the number of data, then you can calculate this quantity, yeah, and then this quantity as well, yeah, and then this quantity as well, and then this quantity as well, and then we can solve two equations, yeah, two unknowns, yeah. So that's can be solved. Yeah? So if you do that, then the beta 1, the point estimate of the slope parameter can be obtained as in shown like here. Yeah. So beta 1 point estimate of beta 1 is the SXY. SXY is the sum of cross differences, yeah, for x and y. Yeah. And then the SXX, sum squared error for the x, is the sum of the differences of x with respect to its mean value, square differences, yeah, over entire data set. Yeah. And then the and then the once the slope beta 1 is obtained, then beta naught, which is the point estimate of the intercept, can be also obtained. Another important things you might want to note in here, for example, this equation, is that the mean value of y and then the mean value of x, yeah, and then a point estimate of slope and then a point estimate of intercept satisfies the linear regression model. Yeah, so that's an important thing. So the point is that the linear regression model always pass through the mean value of x and the mean value of y as a pair. So it passes through the centroid of the data points. So that's another important things to note. So the fitted regression line can be shown or expressed as the y is equal to point estimate of intercept plus point estimate of x slope times x. Yeah, and then for a given particular data xi, yeah, the fitted or the fitted values would be just simply given as in this one, and then for this particular data points, we can define the regression residual, yeah? Which is essentially the data point minus predicted value at the particular value of x. Yeah? And based on this residual, we can define error sum of square. Yeah? So error sum of square can be defined as the sum of the differences between y is the data point, yi hat is the predicted value based on the least linear regression model. Yeah, and then we can expand all those with the y term and then the y square term, yi term, and then the cross term. And then the estimated error variance, yeah, based on the regression analysis is essentially SSE, which is just defined error sum of squares, so the difference of the observation minus fitted values, yeah, and then take square and then the sum, yeah, error sum of squares divided by n minus 2, so the mean squared error, yeah, the total error divided by n minus 2. N minus 2 is the number of free data points, degrees of freedom. Yeah, so initially we had n data, but we used the two constraints to estimate the beta naught and the beta 1. So we reduced the degrees of freedom by 2. Yeah. So this is essentially the mean error squared. Yeah. So in summary, we went through those mathematical derivation, but in summary, we can do the linear regression analysis if we know those 6 quantities. So n, number of data, sum of mean, sum of y, and then sum of squared x, and then sum of squared y, and then a cross term. Yeah. Once we have, then if you look back, you can calculate the beta 1, beta naught, and also error variance based on the all data. Yeah. So then you can constrain the 2 parameter, 2 coefficient. Yeah. And then the error variance, so which you can define the entire regression model in a probabilistic way. The one thing before, I think this slide indeed is important point, and then like we always have to be aware. Yeah, so I just want to emphasize here. So of course, once we have the data, we can fit the model, regression model, to the data, yeah, as we have seen. And then, but again, when you apply those regressed data, you have to pay attention. You have to pay attention to the extrapolation. Yeah. So sometimes the model might needs to be extrapolated to the data range where there's no data in developing those linear regression model. Yeah. So if such kind of situation is necessary, then you need to proceed with caution because the data, the model might fit the data very well within the data range, but like outside of the data range you have, this relation, assumed relation between x and y, which is a linear case, might not be applicable. So yeah, so that is the case for any regression analysis or the model fitting. So please pay attention when you need to do the extrapolation of the model outside of the data you have, then you need to pay attention and then be cautious about doing that. Okay, so let's have a look at the one example. This is for the waste removal problem. Yeah, and then so those are the the problem setup. But essentially, what this example is kind of asking for us to do is that once we have calculated, given the data, and then we have 2 variables to relate, and then we calculated those the summed quantities, yeah, for x, y, x square, and y square. Then we want to determine the regression line and then the error variance. So once we have those 6 quantities, then the beta 1 can be calculated. Yeah. So the x sum of errors for x and y, and the sum of squared error for x. Yeah. So then the beta can be obtained as 0.04. Beta naught also can be calculated. Yeah. And then, so the fitted line, so this is the slope, and then this is the, so this is the slope, here, and then this is the intercept. Yeah. And then the error variance can be also calculated by using those 6 quantities. Yeah. And then the number of degree has to be 20 number of data minus 2, yeah, because we use the 2 degrees to constraint of freedom in estimating beta 1 and beta naught. Let's have a look at another example. So this is the example 68 on the Nile River flow rate. So there's 2 set of flow rate data along the Nile River in Egypt, and then over, I think, more than 100 years. Yeah. And then essentially we have the flow rate in the liver in January and then also the February, and then how those the flow rate in the 2 consecutive months depends. So we have all the data, yeah, from the 1874 to 1988, so more than 100 years. Yeah. And then we can calculate the number various statistics based on the data. Yeah. And then we can first, we should plot the data. So the January data is the explanatory data. So that's the fixed value, yeah, X. And then the Y is something to predict, yeah, so the response variable. And then if we put X and Y, you can see that there's some nice linear features. So you might, at this point, you might decide to fit the linear line. So once that's the setup, then we have those 6 quantities you can calculate, yeah, by using some Excel for that is relatively easy. Yeah. And then we can first calculate the beta 1, yeah, which is found to be about 0.83. And then the beta naught, which is the intercept, which is found to be slightly negative value. And then we can fix the regression line, and then we can plot the regression line onto the data and then compare the data. So the fit looks good from this comparison, visual comparison, yeah, which goes through the center, centroid of the data points, which is around here. And then the error variance can be also calculated from those calculated error statistics. So that is found to be about 0.1. Okay, so that is it for the first session. So we went through the basics of the linear regression. And then by this time, I hope that you understand that how you interpret the linear regression model from the normal distribution perspective. And then also, you know, given the data, you know how to obtain 3 parameters. Beta naught, which is intercept. Beta 1 is the slope, which is most important. And then the error variance, which is a sigma square based on the data. So in the next section, we're going to build a little bit more around what we have discussed today. Thank you.